has one x-intercept, and that's really the key difference before the last example. So one x-intercept here. We can determine the asymptotes of the reciprocal function based on this original function. Now, if you do know, the big theme in this unit is that if the original function has an x-intercept, when we reciprocate that function, that x-intercept becomes a vertical asymptote because it is a restriction because it's now in the denominator when you reciprocate it, so it's no longer allowed to exist at that particular value. So there's one vertical asymptote at x is equal to 3, and that's really the key difference here. We only have one vertical asymptote. Last example, we had 2. Now, horizontal asymptote, there's a shortcut that we learned in the last lesson, and it's because the degree of the numerator is less than the denominator, the horizontal asymptote is y is equal to 0. So it doesn't change. There it is. Now, how do we sketch this? Well, let's look at positive and negative intervals next. We should know by now that those do not change when we reciprocate a function. So when I make this y is equal to x minus 3 squared into 1 over that, the positive versus negative numbers are not affected. It says if something was positive originally, it'll stay positive. Intervals of increase and decrease, we know that that actually does change when we reciprocate a function. Reciprocal function is going to be increasing when the original is decreasing. So right here it's decreasing, so the reciprocal will be increasing. And then of course when the original function is increasing, the reciprocal function will be decreasing. End behavior is the final kind of characteristic that we look at, and let's look at it around the vertical asymptote. So as I approach 3 from the left, so that will be along here, we're going to find a number that's really close to 3 on the left of it. So that will be a number like 2.999. Plug that into the reciprocal function, 1 over the original, and try and figure out what y is. And in this case, it's about 1,000,000. That's a really big number. I'm just going to call it infinity, or we call it infinity. And we write as x approaches 3 from the left side, y approaches positive infinity. That is denoted graphically by this arrow here that's going towards infinity as x approaches 3 from the left. We do the same thing as x approaches 3 from the right side, so that's to the right of the asymptote, and we'll find a number really close to 3 and slightly bigger. So that'll be 3.001. That's the number to pick. Substitute that value into the function, the reciprocal function of course, and solve for the y value, and we get again a really big number, which we're just going to call infinity. We can write as x approaches 3 from the positive side, y approaches positive infinity, and that's denoted by this arrow here that's reaching positive infinity as x approaches 3 from the right. Now let's do the same thing with the horizontal asymptote. And the horizontal asymptote, as we know, is really concerned with x approaching negative infinity, and that's on this end here, and then x approaching positive infinity, which is here. So as x approaches negative infinity, I'm going to plug in a number that's really big for x, and that's going to be negative 1,000. I'll plug that into my reciprocal function or equation and see what my y value is, and it's very, very close to 0, but slightly bigger. So I'm going to say it's approaching 0 from the positive side, and we'll write as x approaches negative infinity, y approaches 0 from the positive side. And where's that? That's right here. The arrow is just above the x-axis. We'll do the same thing with positive infinity and pick a big number like 1,000 for x. You can pick 10,000 if you want. Substitute it into our reciprocal equation, and we'll get the y value is again slightly bigger than 0. So again, we'll say that it approaches 0 from above, and we put a little plus above. So the way we write that is as x approaches positive infinity, y approaches 0 from above. The arrow will be just above that horizontal asymptote here as x approaches positive infinity. So this is a lot of information, and this is really enough to graph this reciprocal function, really just connecting the dots at the end. I'm not doing it really well. This is what a graph will actually do, the actual decimals graph if you use it, graphical software. This is the final example of a reciprocal. So if I have x minus 3 squared plus 2 and try and graph it, there it is right here. This function here does not have an x-intercept, so this is why it's different than all the other functions. We'll start by graphing the original, and there it is. And I've sketched already the vertex and everything. Again, the big thing is that there are no x-intercepts here. So how will that help us determine what the reciprocal looks like? The vertical asymptote, well, because there's no x-intercept, there's not going to be any vertical asymptote. So we were kind of stuck because we will only have the horizontal asymptote. Again, that's still the same. The vertical asymptote does not exist, but the horizontal asymptote is at y is equal to 0. So that is right here. What does the function look like? So the one thing we can do is we can look at positive and negative intervals. And again, that does not change when we reciprocate it. So again, we're still going to be, my graph of the reciprocal will be above the x-axis. Well, that's good. But what will it look like? Intervals of increase and decrease. So what we do know is that when the original function is decreasing, the reciprocal will increase. And similarly, when the original function is increasing, the reciprocal will decrease. So we know that, okay? Now, the good thing is that we know where the minimum is for the original function. It's at 3, 2. Now, that tells us that the reciprocal function will have a maximum, and it's not going to be at 3, 2. The x value stays the same, 3. The y value gets reciprocated, because that's what we're doing here. We're reciprocating a function, so it'll be 1/2. So there's my maximum. Now, the only other thing that we can do is find the end behavior around one horizontal asymptote, and here it's done for you very quickly and untimed, but let me walk you through it. End behavior around a horizontal asymptote as x approaches -infinity, we'll plug in -1000 into the equation of a reciprocal, and we'll end up with y value being, again, really close to 0, but positive. So we're going to call it 0 plus. With that, and that really just means that when I'm approaching -infinity, my y value is getting close to the asymptote, the horizontal asymptote from above. As x approaches positive infinity, I'll throw in 1000 into that reciprocal equation, and I'll end up with a number that's, again, slightly bigger than 0, but it's still very close to 0. So again, I'll write 0 and with a plus kind of exponent looking thingy, but it's not an exponent. It just denotes that it's 0 from above. And that ends up being drawn like this on my graph. So we're approaching 0, the horizontal asymptote, from above. What does the graph actually look like? There it is. We have that maximum with those end behaviors approaching the horizontal asymptote. So a quadratic basically can have 2 x-intercepts, 1 x-intercept or no x-intercepts. We know this from previous studies. This gives rise to 3 different graphs for a reciprocal of a quadratic. All right, so if we have a quadratic with 2 x-intercepts, that's an example right there. We have a quadratic with 1 x-intercept, an example is there. And then, of course, we have a quadratic with no x-intercepts. When we translate that to a reciprocal function, the first case, which is a reciprocal function, the original quadratic at 2 x-intercepts, that means that we'll have a reciprocal with 2 vertical asymptotes. And this is what they will look like. So that's case number 1, and that was the first video. The second one is a reciprocal with just 1 vertical asymptote corresponding to that 1 x-intercept. And it's going to look something like this. And then the third example is a vertical asymptotes that are absent. So there's no vertical asymptotes at all. And that function, the reciprocal function, will look something like this. So it is really helpful to know what the original function looks like, and that can help us graph the reciprocal function. And the huge difference between the 3 cases is the number of vertical asymptotes. So here's an example. We can determine the equation of a graph shown. We can tell that there's only 1 vertical asymptote at x is equal to -4. So we know that a function has a restriction there. The function is a reciprocal of a quadratic. Because of its end behavior, you notice that both ends are kind of on the same side of the graph. There's line symmetry, just like a quadratic. The denominator must be x plus 4 squared, of course, because it is reciprocal of a quadratic. So the simplest equation is y is equal to 1 over x plus 4 squared. And that's good enough. Determinant equation for this graph here, and again we know it's a reciprocal of a quadratic. We're told that, plus we know that this is a characteristic shape of one of our cases. There's no vertical asymptote, so the function has no restrictions. That means that we'll have to look at the minimum here, and the minimum is -1 and -1/4. And that really means that the reciprocal function, or sorry, the original function had a vertex at -1 and -4. And that must have been a maximum, right? Because, of course, a minimum on the reciprocal would have been a maximum on the original. So the original function must be y is equal to x plus 1 squared minus 4. That's the quadratic in a vertex form. A value can be anything. So you can put any value here for a. Of course, it must be positive it must be, we'll talk about this in a second. It'll have to be negative because it is below the x-axis here. And because it's a maximum, of course, so that's why the a value had to be negative. But the function is reciprocal of a quadratic because of its end behavior. And again, I will put in a negative here only because I know that my maximum in my original quadratic must mean that the a value is negative, and that's going to stay on the reciprocal. Last example, determinant equation for this graph shown. We've got two vertical asymptotes, one here at x is equal to 3 and one at x is equal to 2. So now we can easily say, well, the original function must have looked something like this, right? The a value, again, the leading number, could have been anything. We know that it must have been positive because we know that the original function would have been an opening upwards function just because of the way the reciprocal looks like. And the function, the reciprocal then must be 1 over x minus 3 and x minus 2. More examples here, and these are kind of written examples, and you really just have to denote what they mean. So you want to write an equation with a horizontal asymptote at y is equal to 0. Well, that's kind of given. All of them have a horizontal asymptote at y is equal to 0. Vertical asymptotes are at x is equal to -2 and x is equal to 7. So that's pretty easy to figure out. And then you're told that y must be greater than 0 between -infinity and -2 and 7 and +infinity. So two vertical asymptotes, function has two restrictions, x plus 2 and x minus 7 must be those factors, and we'll put those in the denominator. Now the fact that the function is positive or greater than 0 on these intervals between -infinity and -2 and then 7 and +infinity really just gives us an indication of whether there's a plus or a minus at the front here. And because if I sketch it, the above the x-axis is on this side, and above the x-axis is when x is greater than 7. So that's what we're told here in the requirement C. That really tells us that this is what the function looks like, and we know that that must have a positive leading